Welcome to Brain Vision.
In this problem, we're asked to find the required force to keep the block at a constant height. So for this problem, this is going to be my coordinate system. Positive x points to the right and positive y points upwards. Now the components of the acceleration of the smaller block are going to be ax and ay. And so if we draw our force diagram of our block, we have mg pulling down. We have the normal force this way. And since there's no friction, that is it. Now this angle here is our alpha. And so the vertical component of the normal force is equal to n times cosine of alpha. And then the horizontal component of our normal force is n sine alpha. And so sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. And this implies that mass times acceleration in the x direction is equal to the sum of these horizontal forces. And this n times sine of alpha, the x component of the normal force, is the only one. And so we have n times sine of alpha. And we're going to solve this for n. And so this implies that n is equal to m times the acceleration over sine alpha. Now we're going to do the sum of the forces in the y direction. It's equal to mass times the acceleration in the y direction. This implies that negative mg, because it's pointed downwards, plus n times cosine of alpha, because that's the vertical component here, is equal to mass times acceleration in the y. Now, the problem tells us that the acceleration in the y direction of the block must be 0. And so when we plug this into the previous equation that we found, we get that mg is equal to the normal force times the cosine of alpha. Or the normal force is equal to mg over cosine of alpha. Now we have two expressions for the normal force, and we can equate them to one another. And when we do that, we get mg over cosine alpha is equal to mass times acceleration in the x direction over the sine of alpha. Sorry about that. And then now, whenever we solve this for the acceleration of x, we get it's equal to g times tangent of alpha. Tangent because I moved the sine of alpha over, and then I get sine over cosine. I also cancel the m's at this step. Now, if block doesn't move vertically, then both the block and the wedge have to have this acceleration. Remember, the situation is like this. If this is the acceleration of the block, then if the wedge does not have this acceleration as well, then the block will move in the vertical direction, which violates one of our rules. The block has to stay stationary in the vertical direction. And so even though we just calculated the acceleration of the block, it turns out the acceleration of the wedge is also equal to this, where big A is the acceleration of the wedge and little a is the acceleration of the block. Now, the combined system we have to apply force to, and the combined system has a mass of big M plus little m, and the acceleration of the combined system is the same. It's g times tangent of alpha. And so plugging that in, I get that. And this is the force we have to apply to the combined system, m plus little m, in order to get the little block to stay at a constant height. And so this is the final answer to the problem.